we will follow the same pattern as before. Everybody, the speakers have 18 minutes, and then they will get the bell, and then there will be 2 more minutes. And then there will be 5 minutes for questions as usual. Our first speaker is, the first paper is from the China Technical Consultants in Zhongzhen, Taiwan. And the authors are Shang and Wu. The title of the paper is Catalytic Decomposition of 2-butanol over-modified copper zinc oxide catalysts. And the speaker is Dr. Chuang-Sheng Chang.
Thank you, Professor Wu. Ladies and gentlemen, good afternoon. This is my topic, catalytic decomposition of 2-butanol over-modified carbon dioxide catalysis. The spectroscopic studies of D and the reactivation and cell activation. Next slide. Please, next. This is the content of this topic. The first one, alcohol dehydrogenation catalyst is later on. The second one, the deactivation and cell reactivation. 3 is by doing the studies of the instrumental categorization, including the scanning electron microscope, X-ray reflection, solid-state aluminum map and mount, EPR, extend EPR, and finally EPM. And I will give a short summary of these results. The catalytic dehydrogenation of secondary alcohol still is one of the widely practiced industry process and still continuously attract researchers' attention. For most of the secondary alcohol dehydrogenation industry using the copper or zinc-based catalysis. So we will choose these primary studies. For the photo using the copper and zinc oxide catalysis. The first one we're using some tertiary metal oxide to serve as a stabilizer. However, using the aluminum oxide, we will give some desired site reaction, for example, the dehydration. So, try to suppress the dehydration, we will put some kind of basic metal oxide, like the potassium oxide here, to block the oxygen power surface on the catalyst. So, we'll make the alcohol do not absorb there, and it was therefore the potassium suppresses dehydration on the oxygen polar surface by removal of the oxygen back into the site. Next one. However, when we did the certain question, the studies, we found something quite strange. The green line is the catalyst without any promoter, such as the aluminum oxide or the potassium oxide. We can see the conversion of the alcohol increase with an increase on the temperature. With the promoter like the potassium added or the sodium lithium, something strange changes here just after the temperature about 325 degrees centigrade. The same is the conversion gradually increase, but when the temperature reaches 325 degrees centigrade, with the dopant of the sodium, there's the loss in activity. But with the lithium, little loss in activity occurs. But with the potassium, you can see drastically increase of the activity. However, when the temperature goes above 350 degrees centigrade, the activity will raise once again spontaneously, almost change the original label prevailing before the activity loss. So what happened here? Try to do the next first we took the catalyst away out of the reactor. You can see the fresh catalyst is dark black. In the temperature of 300 to 320 degrees, no any catalytic activity loss. The catalyst is still maintained at a brownish color. But when go to much higher temperature, you can see the color changing quite quickly to the yellow-green. And when we take out the catalyst above from 350, the color comes back to the black again. And get a much higher temperature, the color becomes reddish again. So what happened here? This is probably suggested by people before. A transition from the carbon 3D to the zinc oxide forest conduction gas is responsible for the black color. So when we see the color change in our carbon zinc aluminum potassium oxide test, it probably means an environmental change occurred for the carbon upon the variation of the reaction temperature. Here is the pole distribution study. You can see the pole. This is probably not a true pole because the catalyst has been blinded to very fine also. So this is the external one. The internal here probably mainly is the metal pole. Feature is quite similar, but cannot explain for the change in heat. Next one. So we go to the basic quality study here. In the fresh catalyst, the surface is quite smooth, but when you take the catalyst out of the temperature above 350 degrees, you can see the surface becomes much more smooth. But above the 350, it goes back to rough again. So it means something happened there. This is the XRD study. Mainly what we can see is the zinc oxide fraction pattern. Almost no change. These two marked with the red star. This is the metal carbon 101 diffraction band, and the small one is the metal carbon 200 diffraction band. Compared with the fresh catalyst, it is almost the same, and the intensity ratio for the carbon 111 to 200 is about 2 to 1, is what we can expect. However, go to much higher temperature, it gets down to between 1 to 2. And above 350 degrees, you can see it go back again, almost return to 2 to 1 here. So the carbon is really changing. But what about other elements here? Doing with the mass NMR for the aluminum, you can see mainly has two resonance signals. This one, since we use the aqueous aluminum trichloride as the standard, so this one probably is the 6 coordinated aluminum, and this one is the 4-fold environment. All of the experiment shows similar only the chemical shift is a little change. Next one. This is a fresh catalyst. You can see this is in this page. Here is 6-fold, and this is 4-fold. The catalyst taken out from the reaction always has something different chemical shift value from that of the fresh catalyst. However, the data shown here probably do not suggest the aluminum really change or not. And the second thing is we do not really distinguish which one is coming from the surface contribution, even the catalyst has been finely divided. So therefore we think, okay, when we did the TPR, we found something. When these three catalysts are open with different alkaline metal, we did see the different reduction temperature. And furthermore, when we do the reduction pretreatment for the catalyst, probably some copper species still remain in the higher oxidation state and so on. If that's true, we can probably investigate the copper species with EPR, with the copper with nuclear spin quantum numbers 3 over 2, we probably can see something there. That's what we expected. Okay, here for the flash catalyst, only 3 signals occur. B along the whole series, you can see probably is a single quartet here with the copper in the axial symmetry. C and D is quite strange here, we will introduce later. About when the temperature raises to over 320 degrees of centigrade, another broad signal occurs, we call it A. It will growing and growing just when the temperature increases to here the 350 degrees. Above the 350 degrees, it will gradually increase again. But the signal C first it grows and increase till the signal A appears, then it decreases, and above the 350 degrees, when the signal A decreases, the signal C increases again. So what happens there? Let's go to see the signal B first. From here, perpendicular T component and parallel T component seems nearly no any change, as well as they are hyperfine constant. And furthermore, the T parallel component is larger than the perpendicular component, larger than the free electron T value. So we can think that the signal B is really a monomeric copper species in the tetragonal side. This is a partial assignment for the EPR signals. For the signal B, probably is coming from a stronger magnetic dipolar interaction. So it will grow and finally become a small copper oxide cluster. However, it could not be observed by XRD. The signal B with its this is a mistake. Parallel component larger than the perpendicular component, and larger than the free electron T value. So we assign it as the copper ions in the tetragonal side. So it means it's in the bar phase. Signal C with a T value quite close to 2.023. So it means probably it's a free electron trap in the magnet side on the surface of an ion. Signal D with the T value 1.96 is still don't know what is that. Okay, next one. Now we can go back to see again. The signal A will increase till the temperature reaching 350 degrees, and then decrease. However, signal C increase till the 325 degrees, then reduce till the activity lost. Up above the 350 degrees, the signal C will increase again. So the copper species here is really concentrated here. Next one. If we think we probably have some different type of copper species in this catalyst, the first one probably is an isolated copper 2 ions, probably incorporated into or on the catalyst surface. However, we might omit this one and probably located in tetrahedral or octahedral side. The second one is the copper oxide clusters or particles, which is irregularly distributed on the catalyst surface. So we use a diagram to show that. This is the signal A. It's a small copper oxide cluster with a T value almost about 2.6 and without any hyperfine structure. This is in the back phase is the signal B, and some isolated carbon oxide. Their distance is not known. However, some kind of spin interaction might occur if the pool is distribution is there. The green one is some natural carbon species located on the surface. They are EPR silent maximum. So now we can convince ourselves carbon has something. But what happened about what we originally suggested, carbon, zinc oxide, aluminum oxide catalysis, it has a big disadvantage. Mainly it's the low resistance to the thermal shocks, so which does not allow the catalyst to be operated above 300 degrees centigrade, according to the report from SRI next one. So we go to check the next one, the alkaline. Sorry, go back. We go to check the next experiment. What happened for the alkaline metal? This is the EDM-based studies. The target is a photograph of an optical microscope. So you can see some kind of crystalline material grows above on the surface. The diameter is probably over 60 micron. And when you check the EDMA, you can see there's no cover for this crystalline material, as well as this is not a single companion material, the next one. When you go to see the aluminum intermediate, it's definitely potassium-containing, potassium-rich species. So if we mean originally potassium oxide try to suppress the dehydration, it will attach on the aluminum oxide. So replace the OH group to the OK group. So what happened here is the potassium has get out of the aluminum. So next one. If we think the potassium oxide has quite low cutting form, so it means it has very low thermal stability. It may be responsible for the deactivation and cell activation again. Next one. If we think that this is what happened originally on the surface, now the temperature will change it again. The potassium oxide grows like a crystalline. So liquid is one, and it probably may not be distinguishable from the solid state of the next one. The same case we also see in some slow wave containing catalysts. We will not discuss too much in the next one. We give a short summary. The first one is both isolated and clustered carbon oxide ions could be identified by the EPR. Second is the XRD and OMR suggest that the zinc and aluminum matrix remain in no change during the reaction. Three is the EDMA supported crystalline material formed at a high temperature was potassium containing species. Whether it's potassium hydroxide or potassium oxide is still not known. Four is the structural modification to reduce the carbon and the residual carbon oxide species on the catalyst by potassium oxide. It's probably responsible for the observed phenomenon of deactivation and cell reactivation in the presence of alkaline or motor catalyst. Last one is the potassium or zinc or motor catalyst are relatively inferior than those of the sodium or motor. Finally, I think my assistant, Mr. Sherlock Wu, I also thank the discussion of Dr. Jinggu Wang and Zhengong Liu, financial support from CRC, CTCF, and National Science Council. Thank you.
We have time for several questions.
Yes. Correct. A little ketone.
Right.
That's a reaction. The catalyst that we're studying is the purpose of using this catalyst is that the hydrogenation of the
mainly for the dehydrogenation.
I wonder why the alkali components are added into the catalyst at all, because the dehydrogenation function is already present, mild dehydrogenation function is present in the catalyst without any alkali. And usually these alkali are added for other functions, such as coupling of the ketones, base catalyzed reaction.
We will do that.
Indeed.
We will do using the potassium or what other alkali because there's some kind of industrial commercial catalyst using that. We just try to modify that. However, this question is completely solved. We use other methods to solve it, but it's a secret I cannot report here. But before that, we follow using when we try to modify the commercial catalyst, that's the way we use. Do I answer your question?